And welcome back. As we go ahead and get ready to dive into a new concept, that of recursion, let's go ahead and first talk about this by talking about how we can trace a recursive call. So first off, what is recursion? Well, recursion occurs when we have a method definition that includes a call to itself. And we said this is often a recursive call. Like most modern programming languages, Java allows methods to be recursive. Of course, up to this point, most of the designs that we have done have been more iterative. Now, if you use this with a little care, it can be a very useful programming technique. And we're going to introduce some basic methods that are needed for defining successful recursive methods. So let's start first by looking at recursive void methods. When you're writing a method to solve a task, one basic design technique is to break that task into smaller subtasks. Sometimes it turns out that at least one of the subtasks is a smaller example of that same task. If the task, for example, is to search a list for a particular value, you might subdivide this task of searching into the first half of the list and the subtask of searching the second half of the list. The subtasks of searching the halves of the list are therefore smaller versions of that original task. And whenever one task is a smaller version of the original task to be accomplished, you can solve the original version by using a recursive method. So let's look at this through a simple example. And the best way to do this is to look at this with a static method. All right? And of course, one thing to understand is that recursive methods don't have to be static. In Java, a method definition may contain an invocation of a method being defined. In such cases, of course, the method is said to be recursive. And we're going to look at this with an example known as vertical numbers. So we'll see this in a second here, but Recursion Demo 1 contains a demonstration of program for a recursive method named writeVertical, which takes one non-negative integer argument and writes that into the screen, with the digits going down the screen one per line. So the invocation of writeVertical 1, 2, 3, 4 would produce the output 1, 2, 3, and 4, each on their own line of code. So let's break this down just a little bit more. The task to be performed by writeVertical may be broken down to two subtasks. So it's a very simple case. If n is less than 10, write the number to the screen. After all, if the number is only one digit long, the task is relatively simple. Our recursive case, though, is if n is greater than or equal to 10, well, then we have two tasks to do. We have to first output all the digits except for the last digit, and then output the last digit. So let's look at this with a sample input then. If the argument was 1, 2, 3, 4, the first part would be 1, 2, and 3. And the second part would output 4. The decomposition of tasks into subtasks can therefore be used to derive what our method definition should look like. So let's examine those two tasks in more detail. Subtask 1 is a smaller version of our original task, because we just took 1, 2, 3, 4 and turned it into 1, 2, 3. So we can implement this subtask with a recursive call. Subtask 2 is just, of course, our simple case. It's less than 10, so we can just go ahead and just output that number. Thus, an outline of our algorithm for the method writeVertical with a parameter n is given by the following pseudocode. We say if n is less than 10, just print out n. Otherwise, we want to call writeVertical, which is the number n with the last digit removed, and the system out of print line the last digit of n. So let's take that pseudocode now and convert it into actual code that we can use in our program. If you observe the following identities, it's easy to convert this pseudocode to a complete Java method definition. N divided by 10 is the number n with the last digit removed, because remember, it's an integer, so we don't have to worry about decimals and stuff like that kind of messing with things. N modulus 10 will give us the last digit of n, because remember, we're in base 10, so if we just say mod 10, it will simply just return whatever number that is. So if I take 1, 2, 3, 4 and divide by 10, I get 1, 2, 3. And if I take 1, 2, 3, 4 mod 10, I get 4. So let's actually trace our recursive call now. Let's see what happens when the following method call is run as made in the recursive demo 1. So writeVertical 1, 2, 3. When this method call is executed, the computer proceeds just as it would with any other method call. So it's going to take those numbers and plug it back into the method. So the argument 1, 2, 3 is substituted for the parameter n, and the body of the method is executed. After the substitution of 1, 2, 3 for n, the code to be executed is equivalent to if 1, 2, 3 is less than 10, print out 1, 2, 3, else do a right vertical of 1, 2, 3 divided by 10, system out print line 1, 2, 3 mod 10. You can start seeing where this is going here. Because 1, 2, 3 is not less than 10, the else part is what's executed. However, the else part begins with the method call right vertical n divided by 10, which, because n is equal to 1, 2, 3, the call right vertical 1, 2, 3 divided by 10 is equivalent to right vertical 12. When execution reaches this recursive call, the current method computation is placed in suspended animation, and this recursive call is then executed. So we're not going to worry about finishing 1, 2, 3. Instead, we're going to focus on finishing vertical 1, 2. When this recursive call is finished, the execution of the suspended computation will return to that point, and the suspended computation will then continue from there. So once we figure out what vertical 1, 2 is, it's going to be able to come back and finish vertical 1, 2, 3. It can't finish 1, 2, 3 until it has vertical 1, 2. Now the recursive call vertical 1, 2 is handled just like any other method call, just like we saw when we had vertical 1, 2, 3. So the argument 12 is substituting for the parameter n, and the body of the method is executed. After substituting 12 in for n, of course, we have two computations, one suspended and one active, as follows. So if you look here, we have our if statement of 1, 2, 3, and we have our if statement of 12. Because 12, though, is not less than 10, again, we're going to go into the else part. However, as we already saw, and you probably might have predicted, the else part begins with a recursive call. And the argument for the recursive call is n divided by 10, which in this case is equivalent to 12 divided by 10. So the second computation of the method right vertical is suspended, and the following recursive call is then executed. Right vertical, 12 divided by 10, which is equivalent to right vertical 1. At this point, there are two suspended computations. All right, we have the right vertical 1, 2, 3 and right vertical 12 that are waiting to be resumed. And the computer begins to execute this new recursive call, which is handled just like all the rest of them. So now we have right vertical 1 saying, hey, I'm ready to go. So the argument 1 is substituted for the parameter n, and the body of the method is executed. At this point, the computation looks just like the following. So we have this kind of stack of computations with our if 1 is less than 10 on top, then we have if the 12 is less than 10, and then if 1, 2, 3. So again, these are all kind of stacking on top of it. You'll notice there's a little note I left here. So no recursive call, because think about it, because is 1 less than 10? Yes, it is. Well, what's that going to do to our code now? At this point, we keep going into this else statement, but now we're going into the if statement. So what is going to happen? So we're going to output the digit 1 because we have a print line statement there. When the body of the method is executed, something different happens versus what we've been doing for our last few iterations. Because 1 is less than 10, the Boolean expression in the if-else statement is true, so the statement before the else is executed. The statement is simply an output statement that writes the argument 1 to the screen, so the call right vertical 1 writes 1 to the screen and ends without any recursive call. Furthermore, when the call right vertical 1 ends, the suspended computation that was waiting for it to end resumes where the suspended computation left off, as shown by the following. So, of course, we had 1 be printed out, but now, of course, because we know what right vertical 1 can do, we can now kind of resume here with this systemout.println. So we're going to output the digit 2 now. When this suspended computation resumes, it executes an output statement that outputs the value 12 mod 10, of course, which is 2. That ends the computation, but there is yet another suspended computation waiting to resume. When this last suspended computation resumes, the situation is, of course, our if 1, 2, 3 is less than 10. Remember, we're here in the else statement. We're resuming right here at right vertical 1, 2, 3 divided by 10. And now we're at the print line of 1, 2, 3 mod 10. So this is going to, of course, output the digit 3. When this last suspended computation resumes, it outputs the value 1, 2, 3 mod 10, which of course is 3, and the execution of the original method call ends. And sure enough, the digits 1, 2, and 3 have been written to the screen 1 per line in that order. And so here we are over in Eclipse. Let's take a look at how this actually looks with a method call. And so you can see I just have a call here with right vertical. I have right vertical 3, right vertical 1, 2, and right vertical 1, 2, 3. And so just a couple different inputs to kind of test this out. And if you look at our method, you can see here's our if part, which has if n is less than 10, and our else part of the statement, which says right vertical n divide by 10. This, of course, is the recursive call right here that we are working on defining. And then in our print line statement, you can see down here we have n mod 10, which of course is what we want it to eventually do. So if we run this, we get right vertical 3 is just going to return 3. Right vertical 12, we return 1, 2. Right vertical 1, 2, 3 will return 1, 2, 3. So that's pretty cool how that can do that. And we're going to see a lot more examples of how we can use recursion, but I'm going to go ahead and just do one more call here just to go ahead and show you. So if I just do right vertical, let's do something that's not 1, 2, 3. How about we do 5, 6, 7? All right. If we are following our recursive tracing here, you can think about how this has done it. It's going to feed in 5, 6, 7, which means what would we expect to be our output? Well, remember, it's going to first work here at our single case, so it's going to print out that 7, and then it's going to pull apart the 6 and then the 5. And so if I run this, I should see it. Here's our 5, 6, 7 printed out. Now, what if I made this with another digit? So let's just say I make this, how about 4, 5, 6, 7. And so if I rerun this, even though I've added another case to it, now let me just put a print line statement here just so we can kind of see that nice and clean. Oh, forgot my out here. I just got system.print. There we go. If I go ahead and do this, just so you can see it nice and clean, you can see it doesn't matter how many digits I put in here. In fact, I can just put a bunch of numbers in here. It doesn't matter as long as it's still an integer. Notice I do get an error here now because it says it's out of range because my value is too large to be an integer. So I just need to back that up here until we get to a value where it's happy. Oh, there we go. So that will work right there. And so even if I have this really large number, you'll see it will still work because, again, it's using that recursive call to go ahead and handle that appropriately. So these, of course, are things that we have to start addressing and looking at. And this might be a little confusing, but that's okay because we're going to take time to kind of work through how to not only trace these recursive calls, but how to go about developing our own methods.